Check it out now, y'all.
nanoHUB-U, online instruction.
Hello and welcome back to the course Thermal Energy at the Nanoscale. This is Tim Fisher again, and today we are going to proceed into the third lecture of week one, and we are going to discuss lattice vibrations and phonons. And this is a very important lecture because it's kind of the first time we've started to get into some of the mechanics of vibrations, which carry a lot of energy and ultimately lead to properties like thermal conductivity and heat capacity. So we're going to start thinking back to our harmonic approximation that we made with respect to two atoms that were bonded together, and we said that the potential energy that's stored between them is related to their displacement away from the equilibrium point, the bottom of this potential well. So that's shown here. And G is our spring constant, and that's something that we use to signify the strength of the bond. Now, we mentioned earlier that the bond is not perfectly linear, meaning that this spring model doesn't quite work exactly. The spring model is consistent with a harmonic approximation to the bond or to the interaction between the masses, when in fact the blue line that's shown here is the more realistic curve, and any deviation between the harmonic curve and the anharmonic curve is the result of anharmonicity, it's called. And that is something that it is very important for studying and understanding heat transfer by phonons, and especially thermal conductivity. And we'll get to a little bit of that later, but for the most part we can do the vast majority of thermal properties can be extracted and derived by using the harmonic approximation. So that's where we're going to start. And we're going to go back to our one-dimensional chain where each atom is connected by a spring with a spring constant G. And the separation between atoms, because they're all alike, the separation between atoms is the same as the lattice constant A. Now, what we'd like to do is to understand how all of the atoms move together. And that's a difficult problem, as you might expect. There's many atoms moving in different at different frequencies and over different wavelengths. And that's not at all easy to capture, but I think what I hope we'll find today is that the math is really not all that difficult. The biggest hassle, it seems, in teaching this and having the audience understand it is that we have to use sort of a discrete math because the masses are isolated at points and separated by springs. So what we're going to do is we're going to collect all of the harmonic potential energy and sum it over the entire chain of atoms. Now, you can think of that for now, for the time being, as spreading out to infinity. And then pretty soon here we're going to put a constraint on that. But essentially what happens is that once we have a chain of atoms, it's not just about one particular atom's displacement away from equilibrium, because what really matters is the relative displacement of that atom to its nearest neighbors. And that's what's captured in this summation. So now instead of having just that 1/2 G times U squared term, we have to take 1/2 G times a difference between the displacement U at neighboring atoms squared. And then we sum that over the entire chain of atoms, and we can calculate the total harmonic energy, potential energy of the chain. Well, that is somewhat useful, but it's not really the thing we're after. What we'd like to do is to develop an equation of motion for the atom. So one of the things from continuum mechanics I think most people appreciate is that the force can be related to the potential energy. It is actually the derivative of potential energy with respect to position. Now, we're in a discrete world, so we're going to use a little bit of a cumbersome notation for now, and we're going to identify every point as being associated with a position. Every lattice point is associated with a position n times a, where lowercase n is just an index, and then a is once again that lattice constant. So n times a is going to give us the position on the chain in an x coordinate. Now this force which again can be expressed as a spatial derivative of potential energy multiplied by -1 in front, that is also famously equal to mass times acceleration, or mass times the second time derivative of displacement, and that's what this term is right here. So really, F equals ma. I think that we can understand that, and then we're going to convert F to a derivative of energy, and when we do that, we actually have a sequence of terms here. So in this summation above, we actually have to use two terms. If we're going to focus our attention on an atom at a specific position, n times a, actually that n times a atom is going to show up in two of these terms in the summation. And that's where you get this bottom relation. So this is something that I think, if on your own, it would be nice if you could just expand this summation a little bit, and you'd see that, that indeed when I expand it, and then I take a derivative with respect to the displacement at that particular location, not at the others, that will give me the force on that atom at position n times a. So with all of that notation and explanation, what we're going to do is simplify the notation, and we end up with a governing equation that's, again, m times a, mass times acceleration, acceleration expressed in terms of that local displacement and its time derivative. And then that will equal the spring constant times a summation of displacements of the atom at position Na, which has the subscript n now, and its nearest neighbors, n minus 1 and n plus 1. So that's our governing equation, and we would like to solve it. It actually turns out that because of the simplified geometry we have, we can take a generic equation, and that generic equation takes the form of a plane wave, and the plane wave is listed here. This is the standard plane wave solution, e to the I times something k na, where you can think of na as being the x-coordinate, and k is something that's going to be very important to us as we go through this. K, we will find, is what we're going to call the wave vector. And then omega is the frequency. So these atoms will be oscillating, and so omega is a frequency of their oscillation, and t is time. Now, one of the things that I mentioned before that's a little bit cumbersome is this chain going off to infinity. And what we can do to resolve that is just assume that we have a large number, capital N, of atoms, and we will actually connect them in a loop. So this is called the Born-von Karman boundary condition, and we will assume that the ends are connected and that the capital number N is a very large number, so that we don't have to worry about some of the details of a small number of particles. N would be a very large number relative to the atomic chain. So when we plug in that solution, we have boundary conditions. So the boundary conditions that we put on the capital N plus 1th atom, which is also the first atom in the chain, will look like this. So if we just blindly put in capital N plus 1 for the number index, we would come up with this plane wave expression. And then we know that that displacement is also going to equal the displacement of the first atom. And so that's the plane wave solution here. Those two things need to be equal. And so what we find, if they are equal, we just take their ratio. We find that this exponential term, e to the ik capital N times a, has to equal 1. Well, the only way that that can be true is if the argument in its entirety is actually equal to I times 2 pi times an integer, which means that e to the I term is going to be cosine of 2 pi times an integer, and that means that we have a restriction on this wave vector k, this thing that we talked about before, that is related to some integer n. It's an arbitrary integer at this point, lowercase n, and then capital N is the total number of atoms in our chain, and capital N times a is the length of our chain. So if we now think about this k, this wave vector, we can think of that as an inverse wavelength. And in doing so, then the wavelength, the vibration wavelength, will equal the length of the chain, that's a times n, divided by this lowercase n, which is just an arbitrary integer at this point, and could be anything. And so that means that our k wave vector is 2 pi, which is by definition 2 pi divided by the wavelength. We talked about this a little bit earlier. This k, this wave vector, is actually the inverse wavelength. So it's what we replace wavelength with in our inverse or reciprocal space. And so this gives us a restriction on k. So k has to equal 2 pi times n, that's any integer, divided by a times n. And we'll talk about some of the other restrictions a little bit later, but that also then therefore restricts the wavelengths that this chain can handle. We also notice that there is a minimum wavelength. Now, we talked about this before when we argued that reciprocal space is actually a nice thing. It benefits us mathematically. And we said that actually we can't sustain a wavelength of infinitesimal size because we don't have any points or atomic locations or lattice points to sustain wavelengths like that. So our minimum wavelength is actually going to be 2 times the lattice constant, because I would need, if you think about a wave as it proceeds through, and think about a standing wave, it would look like this, and this would be the smallest one. Here's an atom, let's say. Here's an atom, or a lattice point. And you can see that this wave, as it goes through, if it were any smaller than this, it would be having nodes where there are no lattice points. And so it would be kind of meaningless. In fact, we could show that those, any smaller waves than that, are equivalent to longer waves. In other words, they would have the same standing wave nodes at lattice points as longer waves have. So getting back to our governing equation, what happens is we can apply that plane wave solution to our governing equation. And remember, on the left side, on the m times a, mass times acceleration side, we had a second time derivative. So we plug that in and we evaluate it here. On the right side, that was our force term, right? And so we took the derivative of the potential energy as our force expression. The nice thing about this is that when we kind of collect terms and take derivatives, is that we have on both sides, left and right, a term, an imaginary term, e to the I kn minus omega t, that shows up on both sides. And those cancel, of course. And when they cancel, what we've done in essence is we've transformed the equation from the time domain and real space into frequency space, into the frequency domain and reciprocal space, because you'll see that the variable that's still sitting here is k, right? So this k becomes very important. Essentially, it represents the wavelength. What we would like to do is to develop an expression that relates k, the wave vector, to omega, the frequency. So once we have that, then we can kind of understand how fast waves are moving. And again, if you've done any studying of wave theory, you'll know that that embedded in terms like this e to the I k na minus omega t, you have a wave velocity and so forth. And we're going to talk about those in just a moment. What's nice about this very simple problem is that we have an analytic expression for frequency as a function of wave vector k. And that, it turns out, to be a very clean expression. What we're using here, we have this square root term on in the first equality, and then we move over here to the second equality and we have this sine, and we've just used a half angle formula for that. The 1 minus cosine Ka is part of a half angle formula that we can use. And this is a very, very important result, not because it's a sine, or not even because it's simple. It's a relationship that we're going to want and we're going to use repeatedly throughout the course. This is called the dispersion relation. This relates frequency and wave vector, and you can kind of think of that as frequency as being a surrogate for energy and wave vector being a surrogate for wavelength. And this dispersion relation is going to tell us all sorts of things about how energy flows in the material. This particular dispersion relation is specific to something called acoustic phonons. Now, we'll talk about phonons at the end of this lecture, but there are other kinds of phonons as well that we'll get to in later lectures. But right now, I just want you to appreciate that this is the main mechanism for lattice vibrations where we're relating energy and wavelength. The dispersion curve is plotted here, and we'll notice first of all that if we just plug in values of k, the wave vector, and we plot them and let them go to values that are positive and negative without any limit, we'll notice that this is a repeating function, that omega is a repeating function of k. And so therefore, what we find is that if we change k by some factor 2 pi over a, then the displacement is unaffected. And that makes sense. We've actually seen that before. We've seen that that's kind of how we joined the edges of the loop, of the Born-von Karman loop, to give it boundary conditions. So that shouldn't be too surprising. And what we also know from the wavelength relationships that we had, the allowed wavelengths with those integers lowercase n, is that we can only have capital N. Capital N is the number of atoms in the loop. Only capital N values of k are unique. So now we're starting to see that that in real space we had discrete points in our lattice, and now in k space we also have discrete points in our lattice. The way we plotted it here, we plotted it as a continuous function, because usually the value of capital N is very large, and so if we plotted it discretely, it would look pretty much like a line. Now, by convention, in this range of k, and we're going to start calling this k space, in this range of a magnitude 2 pi over a, we're going to take it by convention to lie in between minus pi over a and plus pi over a, and that's what we're plotting here. We've normalized everything. We've also normalized the frequency by the mass and the spring constant. It's interesting to note that in this relation, the peak frequency, which happens when k equals pi over a plus or minus, the peak frequency is simply related to the spring constant and the atomic mass m. And it's 2 times that, in fact. So 2 times their square root, the square root of their ratio. So this is, bringing these things together. I don't want the audience to lose sight of the fact that we're still dealing with some pretty basic concepts, right? A spring constant, mass, right, and wavelengths. And so this is a very important result. We're going to see curves, dispersion curves like this, and use them in our transport calculations routinely. So there are some velocities that go along with any of these propagating wave solutions. So there's a phase velocity. That is just the ratio of frequency to wave vector. The group velocity is certainly the most important velocity that we'll have to deal with. The group velocity is the derivative of frequency with respect to wave vector. The group velocity is so important because that's actually the velocity at which energy transport occurs. And so this is really important, and we're going to see this. We will use the group velocity over and over and over again. If you think back to the first lecture when we talked about the number of modes, that was a factor in our expression for heat flow rate. The group velocity was an essential part of that number of modes, and we'll be able to use that to good effect soon. And then we have the limiting expressions. When k goes to 0, that's for very long waves. We see that there's a linear relationship because that sine function is linear. It asymptotes to a linear function for low values of its argument. So omega is linear with k. That's also an approximation that's very common even for wave vectors that aren't so small. And that's something that we'll see and we'll use as well. And we'll also see that as k goes to 0, the group velocity converges to the phase velocity. So these velocities, especially the long wave velocities, are what carry sound in materials, because sound waves, acoustic sound waves, are very long wave relative to these atomic distances that we're talking about. And that's why these vibration modes are called acoustic vibrations. So a couple of notes here. When we get to the edge of this unique part of k-space, that's plus or minus pi over a, the group velocity goes to 0, because remember, the group velocity is the derivative of frequency with respect to wave vector. I'm going to go back a couple of slides just to show that. You see that up here, the curve flattens out. This is the top of a quarter sine wave, and so a flat spot in the dispersion curve means that the group velocity goes to 0. And we see that here. And what that means, if we actually plug in our plane wave solutions for those specific points in k-space, pi over a, plus or minus, we'll see that we take the ratio of the displacements. Remember, our displacements were governed by this plane wave solution. We plug in that plane wave solution, and we find that the displacements, the ratio of the displacements of nearest neighbors is -1, which means that the displacements are equal and opposite. And what this means is that instead of having the wave propagate through the medium, these neighboring atoms are just vibrating against each other, and they're not going anywhere. And that's why the group velocity is 0. They might have a lot of energy embedded in this mode of vibration, but they're not moving. They're not propagating. This region of k-space that we called the unique part, from minus pi over a to pi over a, is called the first Brillouin zone of this one-dimensional lattice. Now, in higher dimensions, we'll also have a first Brillouin zone. It's the unique part of the reciprocal space. We talked before about why we would want to use reciprocal space. Well, this is a bounded space. There's no infinities here. And the reason that it's unique, the reason that we have upper bounds in magnitude, pi over a, and minus pi over a, is that the lattice can only carry wavelengths of a finite value and higher. And that's why we have this finite region of reciprocal space that we can work with. And you'll see that what we'll do with that is we'll be doing a lot of calculations within that space that would otherwise be more difficult if we used instead a real space type of approach. So to end the lecture today, I want to go through just a few comments about phonons. The word phonon, we haven't said it yet today, maybe once or twice, but we've really been focused on lattice vibrations. And we're going to now introduce this term called phonon, which is a quantum consideration, which is a quantum particle. And I want you to appreciate both the differences and the similarities between classical harmonic oscillator theory and quantum oscillator theory. So if we look back at the classical part here on the left side, we see that we can calculate the classical energy of a harmonic oscillator. This is a mass that's moving back and forth. Now in this case, because it's moving, its energy is actually being manifested as both kinetic energy and potential energy. And so this classical term, this is actually for many oscillators, is going to equal the sum of the masses times the speed, the average speed of the oscillation squared. And this comes from something called the virial theorem that we won't go through in detail, but it's certainly well documented. So then what we'd like to do, since we have some solutions for this displacement, remember those were the plane wave solutions, we can transform that to frequency space and just do a simple substitution. So we have an expression for our classical energy of the harmonic oscillator, and it's going to be related to n, which is the total number of oscillators, m, and then we have, which is the mass. Then we have frequency for a particular wave vector, squared, multiplied by u tilde at that particular wave vector or wavelength. And that u tilde is the amplitude of displacement. Okay, so that's the amplitude, not the, without the time variation in it. Okay. On the quantum side, what we need to do is we need to solve Schrodinger's equation. And what we're showing here is the steady form of Schrodinger's equation. We are not going to do a lot of derivations of Schrodinger equations. Even when we get to electrons, we're going to use the results. This is actually a steady form of Schrodinger's equation. And what you see is that there's a term epsilon here. That's actually the eigenvalue of the problem. So this is the energy eigenvalue of Schrodinger's equation for this quantum oscillator. And what we find is that the energy for a given wavelength or wave vector in the quantum result is equal to some number n sub k, and we're going to talk a lot about that number coming up, but you can think of that as being an occupation number. It's a quantum number that increments in integer values in general, plus a term 1/2 that relates to something called 0 point energy. When temperature goes down to absolute zero, there's still some energy in these quantum elements, in these quantum carriers. And then h bar omega, so h bar omega is the energy of one phonon. So you can kind of think of this as being a phonon. This is the first time I'm really going into details about what that is, but a phonon is just something that is an oscillator that by definition has an energy of h bar times omega. And remember, this is omega at a certain k, so we'll go back to our dispersion relation to find out what omega is if we happen to know what the wave vector is, k. And then n is sort of the number of these h bar omegas, and the term 1/2 is a subtlety of low temperature physics in essence, and usually these n's are much larger than 1/2 or even single digit numbers, and so we won't worry about that 1/2 too much, and it turns out that it cancels anyway in most of the calculations that we do. Now, having said all of that, here's the energy of a quantum oscillator, epsilon sub k. That should equal the term that's being summed over here, not the total summation. And so we substitute, and what we'd like to do here is to develop a relationship between this amplitude of oscillation in the classic harmonic oscillator and the energy here. And so we make these substitutions, equate these energies, and what we find is that the energy is, or the magnitude of the displacement is proportional to n sub k. Actually, the magnitude of displacement squared is proportional to this number n sub k. What this is really saying is that the higher the number of phonons, the more displacement that we get. So in the harmonic case, there's no concept of quantization and number of phonons, but you can kind of see here that the more phonons of this particular energy, h bar omega, that means of this particular wave number also, or wave vector also, that the more of those I have, the larger the classical displacement is. And that's kind of how we, at least I can rationalize in my own mind that there's a link between the number of phonons and the amplitude of the oscillation of the related vibrations at that frequency. So if we look at this a bit more, what we find is that the harmonic, the classical system would allow us to follow, if we took this harmonic curve, that's the black, that's the one that we had before, it would allow us to sit anywhere on that curve. But because we have quantum mechanical particles, these phonons, they can only take discrete values. And those discrete values are each separated by h bar omega. And so this, again, this quantum energy is related to the number of such phonons multiplied by h bar omega and the 1/2 term for 0 point energy. So what we find is, again, that these are intimately related. The phonon is the quantum of crystal vibration energy. The phonon is kind of spread across the crystal. You'll notice that in the last view graph, we saw that the capital number n, the number of atoms, was a part of that calculation. Well, the phonon is sort of spread across the crystal at that vibration. And it's analogous to a photon. It's not, for photons we can know where they are to some extent, but Heisenberg's uncertainty tells us we can't know exactly where they are, and phonons are kind of the same in that respect. And what we see is that this number of phonons, this occupation number, sometimes it's called, is governed by Bose-Einstein statistics. That's going to be the subject of, or statistics in general will be the subject of next week's lectures. But Bose-Einstein statistics look like this, where I have e to the h bar omega, that's the energy, divided by kBt minus 1. So if you look at this, you say, well, if the energy of the phonon is very high relative to the thermal energy, remember that's kBt, then this exponential factor is going to be very large, and the occupation number will therefore be very small. And this is an average occupation number. But if the energy is small relative to the thermal energy, then this number, this denominator, might also be fairly small, and so I could have the possibility of having a fairly large occupation statistic. We'll go through that next week. That's all I have for today. Thanks for your time, and I'll see you at the next lecture.